Hey there. So I just spent about an hour recording part three of the Advent of Code day three video. So if you're new to the series, each day I go through an Advent of Code problem, and I recorded the entire video with no sound, which is hilarious. So instead of uploading 50 minutes of my face moving in a circle with no context, what I decided to do was we're gonna take a look at the solutions. It's gonna be a little bit of a shorter video, and I'm gonna walk you through like the concepts that I used for this. And then hopefully in part four, we'll have audio and we can do more of the traditional like explaining as we go thing. So pro is that it's gonna be a real quick video. The con is that it's gonna be a really quick video. So let's take a look. So as always, I have my solutions here in Ellie. So if you ever want to like see how I did things, oops. So this should give us the number. Okay, so let's take a look at the problem together for part three. Again, I have the stars. I feel horrible. I should have checked my sound. So today's problem, or day three's problem, is called binary diagnostic. And basically what's going on is we have this input of these binary strings, so all these zeros and ones. And what it wanted us to find is the gamma rate and the epsilon rate. So the gamma rate is determined by finding the most common bit in like a column. So if you like look at this column of numbers, there's like 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 0. And the idea is we're going to count up all of those numbers. And here we have 7 ones. And we have 5 zeros. So what they say is, oh, the most common bit's 1. So the first bit of our gamma rate is going to be 1. So you're going to do this 5 times, once for each column. So they get 1 for the first, is 0 for the second, and then they get 1, 1, and 0. Basically just by counting up these columns. So what we did was in part 1, or yeah, part 3.1, what we did for that is, let me just comment out the lines and kind of show you what we did. So starting at the top, we took our input, and our input was just a raw string. So these dash lines in Elm, these are just comments. So I'm just kind of commenting out the transformation. What's nice about Elm is we can like do this piece by piece and kind of walk through things. So I started with the raw input, as I normally do. I'm going to collapse that. I started with the raw input. And the first thing I did was I just kind of trimmed the white space around it so that these new lines in the beginning go away. That's just the way, just to kind of help format the string. And then what we've done in previous videos, and I did it again, was oh, you know what? Let me actually fix this. Okay. We broke apart this string into lines. So now you're going to see for each row in our string, we're going to get basically a list of strings. And then from there, what I did was I broke apart each individual string into a list of characters. So that's what this one does here. And so I'm using the built-in string.tolist function available here. So string.tolist basically takes a string like ABC and gives you a list where each item's a character. Characters and strings are they're pretty close in Elm, but basically double quotes mean strings, and you can have multiple characters, and then single quotes is just a single character like A, B, 0, 1, that kind of thing. So after we did this, we were left with like this list of lists of characters. And so the exciting new thing that we did on day 3 was we went to, Ellie has a built-in like package installer. And we were able to install Elm Community List Extra by searching for it here. So we typed in list extra, showed up, we clicked the install button. And what that gave us access to was a completely new package outside of like the core library here in the Elm docs. Let me go to the top here. So this is the Elm package site. We use this to find like docs when we were like looking up string stuff. Like earlier, we were looking at string to list. That's how we did that. But with this, you can also search for other packages that community members will upload. So list.extra is kind of like, it's got some more stuff in it. And the reason I reached for it was because I wanted to do something to this list that was kind of, it was kind of weird that didn't come with like the normal Elm like core list library, and that is transpose. So I imported list.extra from the top, and that allows me to use transpose here. So what transpose does is right now I've got 12 lists of 12 lists of length 5, and what I want to do is, instead of like going like left to right, top to bottom, I kind of wanted to go like top to bottom, like in column order, left to right. So what transpose does is basically gives us like our column as the first number. So instead of seeing 0, 0, 1, 0, which is, you know, it's over here on the right, instead of seeing that as our first item to match the row, our first item is actually going to be the column. So we'll see 0, 1, 1, 1, 1, 1, 0, 0, 0, whatever, all that stuff. So what transpose does is it's going to give us the column. So if you look at these numbers actually match the column numbers. So now we have fewer lists. We only have 5 lists, but each of those lists are 12. Just like we have 5 columns, we're going to have 5 lists here. So transpose kind of did that weird thing. And what's cool about that is I could make this function called count bits. So count bits is our first function that like we make ourselves that didn't come from a package or from the core Elm library. So let's take a look at that. So what count bits does is it goes through each character one at a time and basically keeps track, like how many zeros did I see, how many ones did I see, and then we're going to use that to figure out like what the gamma value is and what the epsilon value is. So count bits for this basically gave me a list of like all the ones and zeros that I found. So I'm just going to make this tiny. So for our first thing, we saw 7 ones in the column and 5 zeros for the first column. For the second column, we saw 7 zeros and 5 ones, and it continues on. And basically, these are the numbers that we end up using in the puzzle. So as we go, we basically build up, like, did we see more ones or more zeros? And then that gives us a final binary number, and we can use that binary to go into a decimal number. So if you're unfamiliar with binary, binary is like base 2 and decimal is base 10. And all that means is this is just another way to represent like 22. You should totally Google binary if that's a new thing. It's kind of like a weird mind-bending concept, but it's basically a way to represent numbers with only ones and zeros, which is what computers understand, like on or off. So the gamma rate we're able to calculate with that stuff, and then the epsilon rate was like the same thing, but it uses the least common bits. So instead of 1, 0, 1, 1, 0, it's like the opposite. It's like everywhere you saw 1 kind of gets flipped. So then that ends up being 9. So kind of back to our code, I'm going to move this over here. What we were seeing is if we count all the ones and zeros, what we can do is we can call our second function that we're going to define here. Actually, before I go into this one, I should probably show you how count bits works, right? So this is all of count bits. So what it does is it takes our characters and it uses fold L, which is kind of like a reduce from another, if you're from like using JavaScript or another language like that. What it does is it takes each character one at a time. So an example of that is it'll take like 0, and then it'll say, let's take the bit count. So initially it's like set to 0. We haven't found any zeros, we haven't found any ones, so we like hard code this as 0 in the beginning. And then as we find a 0, we're going to basically increment the amount of zeros we found. And this is us just keeping track of what we've seen. So if we run it for all the lists, what we end up with is like the totals. So at the end, it's just kind of like summing up all the zeros, summing up all the ones we found. And then what this is doing here is this is saying like characters can be anything. Like this could be like the letter A. We don't have control over that. There's like a bunch of characters that you can represent. So if we don't see a 0 or a 1, we're just going to ignore the value and basically say we didn't find any zeros or ones, return the bit count as it was when we like called the function, right? So like if we were halfway through it and we had seen 5 zeros and 5 4s, and then we got like the letter Z, like still return 5 zeros and 4s and keep going, because we're not gonna Z is not going to increment the number of ones or zeros we saw. Okay, so when we called that, we were left with like this, and we were able to get the count, and that felt pretty good. But what we need to do next is basically get the gamma number. So I'm going to show you kind of what this looks like for gamma. So what we were able to do is using 2 gamma bits, which is a function we'll walk through together, we're able to like construct the bit string that we actually see them have in the puzzle, like 1 0 1 1 0, and that's exactly what we have here, 1 0 1 1 0. So to gamma bits is just a function that loops through all the bit counts we saw before. So that was like the how many ones, how many zeros we saw, and basically if the amount of ones was greater than the amount of zeros, we're going to record a 1, and if not, then we're going to record a 0. And so by calling this function, we're able to get the gamma. And then there's a similar function called to epsilon bits that did the same thing, but it kind of did the opposite. So it did, if we saw more zeros than ones, we're going to record a 1, because we basically want to see what has the least. So yeah, so that's how that worked. And then we were left with like a weird thing where we had like a list of integers, but we wanted to like turn that into like a binary number. So we were able to find this really great package. We just went to the packages. I didn't know about this package before today. I searched binary, and I kind of like scrolled through till I saw something with like binary in the name that looked good. So this was the first one I saw by ICID Asset. And it looked like the API we needed, right? We have a list of numbers. We want to turn it from integers to a decimal. This shows it also doing other like binary math. We didn't need that, but having from integers and having to decimal was perfect. So what we ended up doing was after we had these numbers, we basically calculated both of them in one function called 2 gamma epsilon bits. And all this does is it just kind of calls both 2 gamma bits, 2 epsilon bits, and stores both of the results so that we can have them both, because we're going to need them at the end to do the final power consumption thing. So so when we get the gamma bits and the epsilon bits, what we want to do is we want to turn that into decimal numbers, so actual integers that we can work with. So that's where this function came in, and this was using the package. So this would take our list of ones and zeros and then turn that into a binary number, and then spit that back out as a decimal number, which is really cool. So this was an awesome package. So that turned those ones and zeros into 9 and 22, which is what the problem was looking for. So 9 and 22, so far so good. And then in order to get the power consumption, what you had to do was you had to multiply the gamma and the epsilon rate. So the last step of the puzzle was to basically make a function called toPowerConsumption, and all it did was it took in this and it spit out a number. So it took in those decimals, and then it took the gamma, the epsilon, multiplied it together, and we got 198. So when we had 198, I went to my puzzle input, and I was able to take my crazy big string of stuff and paste that in. And what I was left with was the correct answer, which for my data set, everyone's data is going to be different. But for mine, it was like 3,958,484. Part 2 was a little bit of a twist. So how all these Advent of Code problems go is they kind of like tweak it at the end and make it a little bit more interesting or a little harder to see like how much you can like adapt to the new thing. So part 2 of the problem, instead of doing gamma and epsilon to find power consumption, you were finding the oxygen generator rating and the CO2 scrubber rating, which is a bunch of words to just mean like we're going to be looking at like the most common values and the least common values and doing this crazy filtering thing. And I'll walk you through what that looks like. So basically what the problem was asking to do is it was saying, okay, we're going to verify the life support rating, which is determined by multiplying the oxygen generator rating by the CO2 scrubber rating. So they are both values that can be found in our report, and finding them is what's tricky. So both values are located using a similar process that involves filtering out values until only one remains. So before searching for either rating value, start with the full list of binary numbers from your diagnostic report and consider just the first bit of those numbers. Then you're going to keep only the numbers selected by something called the bit criteria, which we'll get to, for the type of rating value for which you are searching. Discard numbers that don't match the bit criteria. If you only have one number left, you can stop. This is the rating value for which you're searching. Otherwise, repeat the process and keep considering the next bit to the right. So what happened was the criteria for the oxygen was we're going to look at the first column. And if you remember in the beginning, we had 7 ones and 5 zeros. So you basically try to find the most common value. So if there's 7 ones and 5 zeros, the most common value is going to be 1. And what this is saying is we're going to basically filter out from our whole list only things that start with 1. And then that's going to be the input for the next thing. If we're left with only one result, that's our answer. If not, we're going to go to the second column and we're going to filter things out that only have the most common value of the remaining thing. So this is going to be a bit of a weird one to walk through. But if you kind of go through the example from above, it started with all 12 numbers, and then it only filtered to numbers that started with 1. So let's see if we can walk through that kind of piece by piece. Again, like these links will be in the video, and I'm so sorry that I messed up the recording because you could see me get confused throughout the video. It was a good time. All right, so let's start at the top. So our parsed input, we basically picked up where we left off, which is we took all of those things and we turned them to a list of characters. And then we started doing something a little bit different. So what we did with these is we had something that would convert it to an oxygen and CO2 rating. So rather than doing that, let's just do it for one of them. So to oxygen rating, somehow we got 23. And what we're going to do is we're going to dive into that function and we're going to try to figure out what happened. It was a lot more natural as we kind of gradually built it together in the muted video. But we'll see how I can explain this. Basically what we had to do is we have a function called toRating that we're going to look at. It turns out we reuse this for oxygen and for carbon. And then we do find the most common bit. For oxygen, we find the least common bit. So these are all functions that we've defined ourselves. So find most common bit is just a function, and all it does is it looks at your characters, and if it was more zeros than ones, it'll say, okay, 0 is the most common. And if not, it was 1. And then for least common bit, we say if there were more ones than zeros, then give them 0, because that was the least common, and 1. There was a little catch in the code that said if there's ever a tie for most common, always fall back to 1, and if there's ever a tie for least common, always fall back to 0. So we tried to capture that requirement here by using the equal sign to say that ties always return 0 for least, and by not including equal sign, we let the kind of ties go to 1s here. So that's a little subtle thing that we did with these. But that's these functions. They just compare a list of characters. They use the same count bits function that we defined over here in part 1. And count bits was the one that basically took our characters and gave us all the zeros and ones. So that was something that we already wrote, which was great. So that's those functions. toRating is the kind of confusing one. So how toRating worked is it involved a function called so it took in either the find the most common or find the least common. It took in our list of bits, which we saw earlier. That was our parsed input. This is our list of bits. So it took in all these zeros and ones. And what we had to do was we kept doing the reduce until we were left with just one thing. And that was the interesting kind of confusing function. This is when we had to use recursion to try to figure out how to do things the correct way. So what we tried to do is we tried to get one answer, and that's where you see the maybe. So if it worked, we were left with one list. And let's dive in and reduce bit inputs right now, just to kind of show you what that function did. So here it takes in the first argument that it takes in is find bit. So again, that's the find most common, find least common, depending on who called it. If it was oxygen, this would be the find most common bit function. I took in our index, and so our index, if we go to our puzzle input, is what bit are we looking at? So 0 is the farthest to the left, And then this is like index 1, this is index 2, this is index 3, index 4, and then any index greater than that, like that's out of bounds, and we have code that's going to handle that. So back to reduce bit inputs. We have transposed. So transposed did that cool column flip that we saw in the last part. Maybe bits to count basically took the transposed list and it found which column we were looking at. So if the index was 0, it would basically drop nothing. It would keep the list as is and just grab the first thing. If the index was 3, it would drop the first 3 items, and then whatever was left in the front, that would be like the column we're looking at. So this is just a way to like get the column that we wanted to count bits for. And so if we did have a column for that, we'd use that. And what we would do is we would basically call the function we saw before, either find most common or find least common. And what this would do is this would give us the character that was either the most or the least common. And we were able to use that to filter out the items that didn't start or didn't like have that in there. Start with is actually a bad name now that I look at it. But it's filtering out items where that bit wasn't at this index. Without bit at index is a better name, because that's really what it's doing. Let's take a look at that. So what we did is, in like the first example, we saw 1. Let's see if I can comment something out to show you. Yeah, we're gonna comment this out so I can show you like each step of this as we go. So this will help. Oops. So we start with the bits to count. And I'm going to comment out this also, because this type signature is not going to be correct until we're done. Oops. Oops, debug.toString. Okay. Maybe list of characters, bits to count. Oh, okay. Okay, so all we're gonna do is we're gonna start with transposed. Oh my goodness, what's it complaining about? Sorry, this is like, I just so wish that I got this right. Okay. Reduce bit inputs. Okay, so we're left with parsed input. We're gonna do the 2 oxygen rating. Oxygen rating calls 2 rating. 2 rating, it does all this work. And then basically we're just gonna return, we're just gonna return maybe bits here for a second. Sorry for all the commented out code. It broke my heart that the sound, I was like reviewing the video at the end and I'm like, oh, why am I not making any noise? I'm just gonna comment that out too. Oh my goodness. We're gonna have to comment out all the things. Okay. Okay, so just to be clear, what's happening here is we call reduced bit inputs, and then this is like basically the transpose list. This is like the column, and what we did with that is we basically we'd find like the transposed. Is this right? Is this calling the right thing? Yes. Okay, cool. Yeah, so this would find like our maybe list of inputs. Okay, so transposed was doing this. And so transpose was that like sideways look at things. And what we wanted to do was we were at index 0. So we wanted to basically just get the first item in that list. So the 0, 1, 1, 1, 1. So that's what we got. And then you can imagine if this was called with a 1, instead of getting, go back to transposed, instead of returning the first item in the list, it's going to return the second. So notice the first starts with 0, 1, 1, 1. The second item starts with 0, 1, 0, 0. So if I called this function again, but with this time it being 1, you'll see that it's going to be the second item. It's going to be the 0, 1, 0, 0. So as we go, we're basically like updating that index recursively, and that's what gets our code to work. So to get back to it, what we did here was we said, okay, so we've got our maybe bits to count. Assuming we found like a column that we can do work on. Let me just quickly show you what it would look like if this was nothing. So if we tried to pick like column 10 of our input, like there's only 5 columns. So this is when that would become nothing. Basically, as soon as the index is out of bounds, this is just Elm preventing our program from crashing. So 4 is the highest index we could get at, because there's 0, 1, 2, 3, 4 are like the indexes of these columns. So that's why we have this as a maybe bits. So what we did, so let's go back to 0, is we said, okay, let's take a look at like these maybes. And what we're going to do is, if there's nothing, we're just going to return an empty list. And we'll do that again at the end. This is to let the code compile. And basically, if we do have a column, so if we have this, let's just return that real quick, just so we can see what that looks like. So if I compile this, basically now that just is gone, we're just returning the bits to count directly here. And so what bit did was it counted, it basically found the most common bit for the oxygen, right? So the most common bit for oxygen was 1. But when I did the least common bit, like if I wanted to do the CO2 rating, this would change like what happens here. This would say 0 because that's the least common bit that we found in our bits to count, right? Because there's 7 ones here and there's only 5 zeros. So once we had that bit, we had that value of 1, we use that filter out items. Filter out items, this is a crazy thing. We'll rename this function one last time. Keep items with bit at index. That is a much clearer way to say that. Naming's hard. So what we did after that was we only kept the items in the list that basically started with 1. That's what we did. And that was our first step. This was the moment in the recording where I was like, oh yeah, like we did it. Like we're almost there. Looks like our code's doing the right thing. So just to verify that this is correct, these are the same numbers that we're seeing here, and they all start with 1. So what we were successfully doing was we were filtering out anything where the bit didn't start with a 1. And then the tricky part was here, we needed to figure out what we wanted to do based on how many remaining items we got. So if the data set was weird and something bad happened and we got an empty list, like that means we failed. Like something bad happened, we just put like empty list in there. Same goes for if we didn't have a column, like if somehow we got out of bounds, we return an empty list. So these are like scary kind of like not happy paths. But if we did have a list, like a list where it's just 1 item in the front and nothing else, we just return that. And we said, that's our answer, we're done. But if there's anything else, if there's 2 items, 3 items, 4 items, if there's more than 1 item in the list, then what we had to do was we had to call our function again. We use the same find least common, find most common helper. And then we just incremented our index so that the next thing would move over to column 2. And then we gave it, instead of the full list, we gave it the remaining items that we calculated here. And when we did that, we ended up with basically our single remaining entry, which had like the most popular or the most common things in all those places. So that was the 10111 that we found here. So 10111 translates to 23. So for the final bit, basically after I got here, what I did was I had like the find most common hard coded in here. I extracted that out and I like basically made that like a variable that you could pass in. So oops, I do something wrong. Yeah, I did. I need to make this Go all the way to the edge. Cool. So I did that, and then the final step, then now that I had those maybe bits, I try to get the list head, like the item in the list. Again, this would fail if we hit that weird like empty list case. We'd end up with a nothing. So I was happy to find out that I had a just here. So what this was about was really getting those characters, and then I turned the list of characters into a list of strings. We'll do this together. So I turn the list of characters into a list of strings. So you'll see these double quotes become, or these single quotes become double quotes. I used Elm's built-in string to int, as well as filter map, which we saw in the first video. And that basically got us from strings to ints. And since all those parsed okay, they all stuck around. And then what I did was I was able to convert these numbers into this binary value with that API. And this is what it's storing under the hood, like bits, true or false. And then with the binary to decimal, I was able to convert that to a decimal number, which was 23, which is perfect because that's the decimal that we were looking for in the puzzle. So I felt like we were pretty good, and I just needed to do the same thing for CO2. So all that stuff we saw, this was all, I'm gonna add these type annotations back in. Just so you know, I only commented those out because I was tweaking what the functions were returning, and I didn't want to get any compiler errors saying like, hey, like you're giving me like a list of integers. Like I need a list of, you know, a maybe number. I didn't want to deal with all that as I was breaking things down. Okay, so to oxygen rating was that, and then I did the same thing to CO2 rating. I made a similar function. And basically these two functions, to oxygen rating and to CO2 rating, reuse the same logic. They just specified a different like method for like filtering out the numbers. And so they're really like super similar code. And then I had one function that basically called both of them. This was kind of like what we saw with gamma and epsilon in part 1, where we had our to gamma function, we had our to epsilon, and then we kind of had one that put it in a record so that we could keep track of both. And so ultimately that's what my answer uses in the LE. So I was left with just 10 and just 23. And so here we got 23 for the example and 10. So I was like, okay, that's great. Now I need to like get to the 230. And so how am I going to get to the 230 when I've got this record of like maybe integers? So I made a function called toLifeSupportRating. And we gave this a type alias so we could call it, you know, something. But basically this record, we call that life support stats. So this function to oxygen and CO2 rating spit out those stats. The oxygen may be in and the CO2 may be in. And then to life support rating was like the final step. So we took that in, whatever the oxygen rating was, whatever the CO2 rating was, and we converted that to a maybe integer. So before what we did, we had that just 10 and just 23. We reached for maybe.map2. And maybe.map2 takes two maybe values, and if they're both okay, if they both have like just a number, we decide to like multiply them together. If one of them is a failure, that sounds so harsh. If one of them failed, for example, let's say like CO2, something went wrong and we got nothing, basically the whole result would be nothing. But fortunately, both results succeeded, and we're able to multiply those numbers together to get just 230. And so then I looked at 230 and I looked at what the answer was, and it was 230. And I'm like, great. So it looks like the multiplication worked. And then I got my puzzle input. I replaced all these numbers with it, pasted it. I got a really, really big number, and it was 1,613,181. And that was day 3. Again, super sorry that I didn't actually get the traditional like working through the problem. So this is my second recording of the video. There's audio this time. I can see the bars moving. But if you've been enjoying the video so far, please let me know. I had a great comment yesterday where someone like asked a question about custom types, and just like if you have any questions like that, I'll have links to the Elm Slack. You can reach out to me at Ryan. You can follow me on Twitter, RHG_dev. And if you subscribe to this video or this playlist or whatever, I'll be releasing these as much as I can because I'm having a blast with this. This is a pretty good time. And hopefully this will be the last video where I don't record sound. So again, thank you so much for watching. And yeah, happy advent of code. I'll see ya for day 4.